Hello, and welcome to Lesson 2, Part 1 of CE 3305, Engineering Fluid Mechanics. Lesson 2 consists of an examination of fluid properties, the difference between an intensive and an extensive property. There'll be a component where we develop the conceptual theory behind the term viscosity, and a few applications of fluid properties. We'll also examine the toolkit, which contains the ability to access some of the tables that are presented in the textbook electronically, mostly as a way to enhance the speed of things. The notes for the lesson are contained here, and the video links, including this one, is contained in video links. By the time you watch the video, these links will be populated. The link to the Moodle site is in the usual place, and as far as I know, at the time of this recording, there are no supplemental data, Excel worksheets, or scripts associated with this lesson and this part 1 of lesson 2. So the main chapter that we're referring to is Chapter 2, Fluid Properties, and here is a screen capture of relevant portions of the chapter. You'll need to read about system boundaries. It's fairly important. We're not going to dwell on that in the video lecture. You can read that on your own. The boundary has a pretty big impact on how we analyze a system and infer its behavior under different conditions. An important concept that we'll be considering throughout this and future lessons is the concept of state. What is the state of a system? And this picture here shows a system in two different states. The system in this case is the mass contained in this vessel. And in state 1, there's a certain pressure, temperature, volume, and this piston is pushed down so that in state 2, the same mass is present in the system, but there are different volume and consequent pressure and temperature. One of the important equations of state that you've already had in other classes and will certainly be referred to in this one is the ideal gas law. Okay, with that in mind, let us proceed. So, fluid properties, these are properties that describe a fluid. Things like its mass, volume, pressure, specific heat, and such would describe a fluid. There's intensive and extensive properties. Now the extensive properties refer to an entire system. And usually an entire system is described by its total mass. Other properties presumably could be used, but mass is the common one. So let's consider an entire system ourselves. Most of us probably have a mass of 60 to 90 kilos. We are a system. And so our mass, Mr. Stick Dude, is total mass on a balance, although I guess this is a sketch of a scale, is the mass of entire stick dude. Maybe it's, we'll make him a heavy dude, 90 kilograms. Okay, so his extensive property is mass. This body, if we were to tie a weight to it and pull him under water, would displace a certain amount of water. So he has a mass, a volume, and other things. So that's an extensive property, and the way to remember it is it extends to the entire system. Now, if we're to take a spoon and scoop a piece of the body here out, so there's body gunk. The volume of this gunk is 1 spoonful, and it could have its own mass. So if we take that spoonful, put it onto its measuring device, it has some different mass, 1/10 of a kilogram. I'm making the number up. Okay, so the intensive property is generally the refers to a system component. So this entire body is comprised of a collection of spoonfuls, thousands of them. Any one spoonful is an individual component, and the properties relate back to the boundary of the entire system as well as to the component boundary. And so we would say that this intensive property might be mass per spoonful, which is a mass per volume, and that's called density. And that description is the main description of the difference between an intensive and an extensive property. So we'll examine a few of these. That are common. Okay, consider the weight of an object. The weight is an extensive property because it has to be referenced with regards to the entire system. A human being has a certain weight. In U.S. customary, that's usually measured in pounds. When you go to a doctor, they don't cut your toe off and weigh it and then multiply by the equivalent volume or the 10,000 toe weights to come up to your body weight. They might want to do that because I'm sure they'd get a greater copay that way, but that's not what they do. So they measure your entire weight of the entire system, which is your body. If they were to cut your toes off and just weigh your toes and then measure how many toes it takes to make up a body, that's called the specific weight. And that is a weight per volume. Let's look at mass. So the total mass usually refers to the extensive property extending for the entire system, and the mass per unit volume is the equivalent intensive property. Some other ones would be specific gravity, and I think the usual symbol is Sg, and that's the mass of the substance, the specific weight of the substance compared to the specific weight of water. And specific gravity is used a lot in water and other liquid-related comparisons. The ratio or the relationship of specific weight to density is the same as the relationship of weight to mass. We know that weight is equal to mass times gravitational acceleration. Hence, specific weight is going to equal mass over volume times gravitational acceleration, which we've already seen as density times gravitational acceleration. This relationship, gamma equals rho g, is fairly common and important in fluid mechanics. Let's examine one more set of sketches to illustrate the idea of intensive and extensive property. Imagine, if you will, a container of water, and we put it on a scale, and the scale reads something. Okay, so there's our container of water, and we'll pretend that it's reading 8.3 pounds, not including the weight of the container, so that's roughly 1 gallon. Okay, now we take from that water a small portion, about 30 cubic centimeters, which is roughly an ounce. We put it onto a scale, we read its weight, and it's reading 0.065 pounds. Okay, so this is an example to illustrate the relationship between the extensive property, the weight of the entire gallon, and an intensive property, the weight of water per ounce or per some other volume. Okay, so let's summarize what we have. 1 gallon weighs 8.3 pounds. 30 cc's, when we weigh it, weighs 0.065 pounds. If we were to write the specific weight of the water, simply be specific weight based on the gallon is 8.3 pounds per 1 gallon, and we'd write that as 8.3 pounds per gallon. If we write the specific weight based on the 30 cc's, we have 0.065 pounds per 30 cc's. We convert 30 cc's into ounces of volumetric ounces, and there are 128 ounces in 1 gallon. And what do you think we get? We get 8.32 pounds per gallon based on the sample. So the specific weight, the intensive property, is 8.3 pounds per gallon. It doesn't matter if we used a 30 cc sample or the entire gallon to make that calculation. The specific weight is the intensive property. The extensive property of the gallon is 8.3 pounds, and we could certainly consider the extensive property of the 30 cc's is 0.065 pounds. But when we normalize, in this case by the volume, the resulting property is called an intensive property. Later on, we're going to examine something called the Reynolds transport theorem, which is a computational analytical tool that allows us to efficiently map between intensive and extensive property behavior for systems involving mass, momentum, energy, and so forth. So the difference between an intensive and extensive property is an important concept to bear in mind. Okay, we've already examined the fluid properties involving mass. Those are the mass density, rho, which is mass per unit volume. They're related, and the specific weight, which is the weight per unit volume. And they're related to one another through the gravitational component of this, through the constant of gravitational acceleration. We also examine specific gravity, which is the ratio of the specific weight of fluid to the specific weight of water. Now, in some fluids, we have density is some function of the applied stress, applied normal stress. And where this is true, so I'm writing density as the density function of applied normal stress. Let me draw my fluid element really quickly to see what we mean by normal stress. There's my area, and we apply a force normal to the area. So this F over A in this drawing is the normal stress. And we routinely know this as pressure. And probably would call it normal stress, but Freddie Mercury couldn't make that fit really good into a song, so we stick with pressure. Okay, this relationship's somewhat true for, is true for all fluids. Everything is compressible, but if the rho of P is nearly a constant, so change in rho with the change in pressure is small, that's called incompressible. Change in rho, change in pressure is not small. That's called compressible. Let's use water as an example and examine this concept. So what we're going to do is we'll look at the we'll record density. I think we can get this from the from a table online. No. Hopefully this is the back of the book. No, not what I want. What I'm looking for is tables in the back of the book. There should be a table where we can look at the density of material at two different pressures and make the determination as to whether or not that material is substantially compressible or not. The one I want to use is water, because at terrestrial temperatures and pressures that we normally deal with, water is more or less incompressible. Density versus pressure. Well, we can use this table to infer some behavior. So liquid water at 0 degrees Celsius, so that's water that's at freezing temperature but has not phase changed yet, exerts a vapor pressure of 611 newtons per meter squared. So that's how much water pushes against the air phase. We raise that temperature up to 100 degrees, and it's 101.3 newtons per meter squared. Essentially, it's 1 atmosphere, and so this water is just about to phase change, flash into liquid. And now let's look at the density. So the density of water at 101.325 at 611 pascals is 1,000 kilograms per meter cubed. So I'm writing this down. So we have rho at 611 pascals equals 1,000 kilograms per meter cubed, and we'll go back up to its boiling point. Rho at 101 300 pascals is 958 kilograms per meter cubed. Okay, so here is some information for water, and that's inferred from its vapor pressure. And the ratio between 101 and 6 is 6 times 10 is like 15. So a 15-fold increase in pressure on the water causes less than 0.2% change in density. So we would say this is incompressible. And if you want to do it in numbers, because everyone loves numbers, so we have change in pressure was 101 300 minus 611, and the 958 minus 1,000, I can come up with, that is 2, that's 42, and 101 300 minus 611, can't do that in my head. Here we go. Over 100,689. And that would be our change in pressure, change in density with change in pressure. Should have a calculator here in my toolkit. Calculator later. Okay, so I have 42 divided by 100,689. So delta rho delta P is minus 0.000417. Arguably, that's small, so we would treat that as incompressible. Now let's see if we can find a table of another material. So this was for water. Something that's a little more compressible, but not a gas. Hopefully they'll have something in there for like gasoline. Okay, we will skip that. But for materials where the change in pressure with change in density is small are called incompressible. And that has some consequences in engineering design. Okay, there's also thermal properties associated with fluids. And actually, if we examine very carefully that last table we were at, there's something called specific heat. And the symbol our book uses, I believe, is C. And that's the amount of heat that has to be added to a unit mass of fluid to raise the temperature by 1 degree. And the units of specific heat vary if they're the imperial system or in the SI system. C is equal to the added heat per mass, and it raises the temperature 1 degree Fahrenheit or 1 degree Celsius. If we're in the imperial system, the units of heat are BTUs per pound. There's other units, but that would be imperial. If we're in the SI system, the change in temperature would be in degrees Celsius or Kelvin. And the equivalent imperial is degrees Rankine. So those are the ones that are absolute temperature scale. So imperial, and then kilojoules per kilogram is pretty typical for SI. The specific heat, in addition to showing here it's kind of looking like a constant, it also depends on what the temperature change itself is, what the delta T, and if the material goes through a phase change. So phase change would be liquid to gas. In that case, it's called vaporization. It goes gas to liquid. That'd be for cooling, usually, called fusion. And there's also a concept of fusion, going from liquid to solid. And then going from solid to liquid, vaporization, the word doesn't make sense, but it would have the same relationship. If a phase change occurs, the specific heat required to get it over the phase change can be substantial. For instance, to take water from freezing liquid to boiling liquid, so we're at 32 degrees Fahrenheit, 212 degrees Fahrenheit. The amount of heat added here is a couple of 2 BTUs per pound per degree Fahrenheit. I think that's what it is to raise the temperature. But to go from boiling liquid to boiling gas, still at 212 degrees Fahrenheit, it's like about 9,000 BTUs per pound. Okay, so raising temperature is important, but to get the phase change, at least with water, is a substance that takes an incredible input of energy. These are all approximate. Okay, another energy property is called the specific internal energy. Our book uses the symbol U, and that's the energy that a substance possesses because of its state of molecular activity. There's also specific enthalpy, which is the energy a substance has as a combination of its internal energy plus applied normal stress. So enthalpy is usually the symbol H, and it equals U plus P over rho. So where we're at roughly in the textbooks around page 51. And we will go take a look at that real quickly. So here's the specific heat, internal energy, enthalpy, and the authors have a very nice description of that. Now I want to return to something called the equation of state for gas to examine that in some detail. And that's actually the end of chapter 1. Okay, there's where gas law. Dagnammit. Okay, so there's something that we're familiar with from other classes called the ideal gas law, and it is an equation of state. And what it does is it describes, it's a relationship that describes the state of a mass of gas based on its thermodynamic and mechanical variables. And so the ideal gas law, you may have learned it, most likely you had it in this form right here. Pressure times volume is the number of moles times the gas constant times temperature. The way I was taught it is, oh, I just lied. Here we are, where it's, I was taught in the mass form, so PV equals M over cap M RT, where cap M is the molecular weight of the gas, or the molecules of the gas, and M is the mass. T is temperature, V is volume, P is pressure, and I learned it as pressure is expressed in atmospheres, volume is in liters, and temperature is in degrees Kelvin. So liter atmospheres per Kelvin mole will be the units of R, the ideal gas constant. And the way I memorize it is this. It's equation 1.10, I guess. And here's a table that has the different ways of representing it. And this is the mole form. And frankly, in practice, in my opinion, it's relatively straightforward to convert whatever units you have into the molar form of the gas law, make any necessary calculations, and then convert it back. Okay, so the ideal gas law is an equation of state. And the molar form is P V equals M over cap M R T. This is the universal gas constant. That's the mass. That's the molecular weight. And that's an example of an equation of state. We'll encounter other ones in this class, and there's similar equations of state. You certainly encountered it in solid mechanics. Relationship, Young's modulus and Poisson ratio combined together are essentially an equation of state for solid materials. And it tells how applied stress causes deformation of the material. Now with solids, we don't have the concerns about flow per se, and there's some other things that are different, not simplified, but different. Okay, continuing on, there's something called a constant volume specific heat and a constant pressure specific heat. Constant volume specific heat is exactly what it sounds like. It's the specific heat required to change the state of a substance while the volume is held constant. And a constant pressure is the case where the pressure is held constant. Let's examine, just discussion-wise, the behavior of that. If we have the constant volume case, we have this. We have the volume is equal to M over M R T times 1 over the pressure. And constant volume means that's a constant. So, if we apply heat, what will change is the temperature. The number of moles involved doesn't change. The ideal gas loss constant doesn't change. So if we add heat, we expect the temperature to increase. To maintain the constant volume, for the temperature to increase, the pressure has to increase at the same rate, so that T over P, the ratio, doesn't change, and that will maintain a constant volume. Now when we have constant pressure, we have this situation. For the pressure to remain constant, if we raise the temperature, the volume has to increase at the same rate to maintain a constant pressure. So with constant pressure specific heat, volume is changing. The way to imagine that is we start with an initial mass here. There's a piston there. We add heat and its new state. The volume would have had to increase. Oh, I need to put the same load on here to maintain a constant pressure, so it's pushing against the same load. In the case of a constant volume, if we increase the temperature, the pressure has to increase. So that's an interesting use of the concepts related in the equation of state via the ideal gas law. Okay, so that concludes part 1 of lesson 2. Part 2 is going to be on viscosity, and it seems prudent to make that as a separate video, give you time to absorb these ideas and do some reading. So thank you for your attention, and I look forward to seeing you in lesson 2, part 2. Bye-bye.